Okay, welcome back, young students of chemistry. So today what we're going to look at is pH, the pH scale, and how do you calculate pH for particular concentrations of strong acids and strong bases. You remember from yesterday that we talked about one of the definitions of acids is that acids form hydronium and bases form hydroxide. When you're approaching a pH problem, it's really important that you remember that and that you choose the right equation or the right mathematical formula to use for the calculation based on the fact that acids are hydrogen donors, they form hydronium. Bases are hydrogen acceptors, they form hydroxide. So let's get into a little bit about the pH scale. You've probably heard the word pH before. And pH, the scale was just developed by a beer company. They wanted to have a little bit of consistency in their product, so they developed or asked someone to develop this pH scale for them.
Can I have someone from custodial staff call the main office 1127, please? Someone from custodial staff 1127. Thank you.
I don't know if you heard that. They're honking on that overhead speaker. Anyway, sorry. So this Danish beer company had this Mr. Sorensen developed a pH scale, and pH measures acidity. So pH is really measuring an acid. And we know that acids produce the ion, right? Acids produce the ion hydronium. And strong acids, when they are in water, will completely ionize into hydronium. So pH is really a measure of the hydronium ion. And because we're looking at hydronium ion, we will measure pH by looking at the concentration of hydronium. Right? P, H, H is for an acid. Acids produce hydronium. Now the scale has a lot to do with something called the autoionization of water. And that's the equation that's listed below here. Remember, these arrows are reversed. But water, in and of itself, forms hydronium and hydroxide ion. And next unit, we're going to talk a little bit more about the autoionization of water and something that's called the KW, or the equilibrium constant for water. But what is important to know is that water is neutral with a pH of 7. And what that means is that the concentration of hydronium ions is 10 raised to the negative 7, and the concentration of hydroxide ions is 10 raised to the negative 7 when the pH is 7. So you can determine just by looking at the concentration of an ion whether it's going to be acidic, basic, or neutral without even calculating any pHs. Because we know that if we have a hydronium concentration that's greater than a hydroxide concentration, then that means that that solution is going to be acidic. If we, of course, have a hydronium ion concentration that is less than a hydroxide ion concentration, we then would know that that solution is basic. And then to both of those, you can compare them to this 1 times 10 to the negative 7. And if the hydronium concentration is greater than 1 times 10 to the negative 7, then you know that that's going to be an acid because pH of 7 has hydronium concentration 10 to the negative 7. So there's a few ways of determining if something is acidic or alkaline without actually using the pH calculation. But we are going to do calculations for strong acids and strong bases, and these are the equations that you need to memorize. you're going to do the opposite of the logarithm of the concentration of hydronium. These brackets mean specifically molar concentration. So if pH measures acidity, pOH measures alkalinity, because what makes hydroxide ions? Bases do. Let me make sure I'm not spelling alkalinity correct. So pH measures acidity, and that's the opposite of the logarithm of hydronium, what acids make. pOH measures alkalinity, and it's the opposite of the logarithm of hydroxide concentration, which is what bases make. And then we have this relationship that if you multiply the concentration of hydroxide times the concentration of hydronium, you will get the value 1 times 10 to the negative 14. That comes from the autoionization of water. And then we know that pH plus pOH equals 14. That has to do with the logarithm of the number 1 times 10 to the negative 14. So here's what's important to do when you're looking at a pH problem. You first have to identify whether the substance is an acid or a base. Because if it's an acid, you'll calculate pH directly from the concentration of hydronium. But if it is a base, you will first calculate pOH, and then you will calculate pH. And then know that for a strong acid, because they completely ionize, the concentration of hydronium is equal to the molar concentration of the acid. So if I say you have 0.2 molar hydrochloric acid, that means that you have 0.2 molar hydronium, and to get the pH, you'll do the opposite of the logarithm of 0.2 molar. If it's a base, you have to consider how many hydroxide ions are in that base. So if you have a hydroxide, a strong base is from family 1A or 2A. If you have a hydroxide of family 2A, for example, calcium hydroxide, this compound will dissociate much like a salt does. So in the water, the calcium hydroxide dissociates into calcium ion and hydroxide ion. And that makes 2 hydroxides for every 1 calcium hydroxide. So you have to consider that sometimes we're going to have to take the concentration of the strong base and multiply it by 2. And then once we know the concentration of the hydroxide ion, then we will use the pOH, because that is a base, and pOH measures alkalinity, and then we can use our equation pH plus pOH equals 14 to get the pH. We tend to get pH rather than pOH in the final, because that's something that people are more comfortable with. Everyone's heard of the pH scale. No one's heard of the pOH scale. Okay, let's do a couple of problems together. It says for each of the following, we're going to calculate pH, pOH, hydronium, and hydroxide. Now, you don't always have to calculate all of those things, but in this case, I want you to have the practice of doing it all. Now, I told you that the first question that you need to ask yourself is, what do I have? Do I have an acid or do I have a base? So in problem number 1, it says the hydroxide ion concentration is 6.4 times 10 to the negative 5. This number is a number that's greater than 7, so this substance has, greater than 1 times 10 to the negative 7. So this substance in number 1 has more hydroxide ions than water, which means that this is a base. And because what we have is a hydroxide ion, and this is a base, we've been given the hydroxide concentration 6.4 times 10 to the negative 5 molar. So then we
And the formula for POH equals opposite of the logarithm of hydroxide concentration. Therefore, this pH is opposite of the logarithm of 6.4 times 10 to the negative 5 molar. So in your calculator, ladies and gentlemen, it's basically two buttons. If you find the logarithm button, that is generally to the left of the 7, you're just going to put in your calculator negative logarithm 6.4 exponent negative 5. And you should come up with a POH of 4. And let's talk about significant digits. This number, 6.4 times 10 to the negative 5, has two significant digits. So we will report 2 decimal places in our pH. So I'm going to say 6.19 is the POH. I think I just said 6. I meant 4.19. And now to calculate the pH, that's easy. Because we have POH. We know that pH plus POH equals 14. And we can plunk as many decimals on that as we want. That's a definition. Therefore, pH equals 14 minus 4.19. That gives us a pH of 9.81, which matches our prediction that this thing is a base, given the information that was provided. And now to get the hydronium ion concentration, we'll consider the formula from the front of your sheet. It says hydronium ion concentration times hydroxide concentration equals 1 times 10 to the negative 14. Solving for hydronium concentration, that's equal to 1 times 10 to the negative 14 divided by hydroxide concentration. I'm just going to go ahead and put this in the calculator because I'm running out of space here. You should be doing this as we go along, double checking your work. And I'm getting a hydronium concentration of 1.6 times 10 to the negative 10 molar for that. Okay, so the first thing we did was consider whether our compound was an acid or a base. That told us whether we were given hydronium or hydroxide ion concentration. And from that, we decided whether we were going to calculate the pH or the POH. And then we decided how we would get our concentration of the ion that was missing at this point. Example number 2, and again, we're calculating pH, POH, hydronium concentration. Remember those brackets mean concentration of, and hydroxide concentration. We're given 0.75 molar HNO3. With an H out front, that tells us this is an acid. And ladies and gentlemen, acids make hydronium. And because acids make hydronium, we will use the pH calculation we will use this acid to get our concentration of hydronium. So this concentration, 0.75, this is the concentration of hydronium. In a VDA chart, all of that nitric acid goes away and produces hydronium. So because we've got an acid here, we've been given the concentration of hydronium. I'm just going to plug that in over here. And from that, we will calculate pH. pH equals the opposite of the logarithm of hydronium concentration. So in this case, pH equals the opposite of the logarithm of 0.75 molar. Again, in your calculator, you'll just put negative log 0.75, and you get a pH of 0.12 show you another way to calculate hydroxide ion concentration, and you can do this for hydronium as well. You can use the equation hydronium concentration times hydroxide concentration equals 1 times 10 to the negative 14. You know what, we're going to stick with that. I'm not going to show you the other right now. I want to be with you when I show you that. But, so if we want hydroxide concentration, we'll do 1 times 10 to the negative 14 divided by 0.75 molar, which is the concentration of the hydronium. And that gives us a hydroxide concentration of 1.3 times 10 to the negative 14 molars. Hope you're doing okay. Example number 3. You can stampede ahead. You should do that. Just check your work as I finish up. If you can't stampede ahead, you should probably start thinking about what is she going to do next. So the first question we'll ask ourselves is, do we have an acid or a base? We're given a hydronium concentration of 0.00118 molar. So that's one, if we put that in scientific notation, that's 1.18 times 10 to the negative 3 molar. That number is greater than 1 times 10 to the negative 7. Remember, we're comparing it to 1 times 10 to the negative 7 because that's the amount of hydronium that's present in pure water with a pH of 7. This number is greater than 10 to the negative 7, so it's got more hydronium than neutral water has, which means this is likely an acid. Either way, what we've been given is the hydronium concentration. So pH equals the opposite of the log of 1 times 10 to the negative third. Remember, pH is a negative log of hydronium concentration, and we were told that that's what we were given. So negative log 0.00118. And that gives us a pH of, let's see, 2 significant digits, 3 significant digits, so 3 decimal places, 2.928. And does that make sense? Yes. We know it's an acid because the concentration is greater than the hydronium concentration in water, which means it's going to have a lower pH. It's going to be more acidic. So then, of course, to get the POH equals 14 minus 2.928. I'm going to start picking up the base here. And that gives us a POH of 11.072. The hydronium concentration was given as 0.00118, and the hydroxide concentration is equal to 1 times 10 to the negative 14 over hydronium concentration 0.00118. So the hydroxide concentration is 8.47 times 10 to the negative 12, and let's plump a unit on there. That's a molar concentration. That's what the brackets mean. is negative 0.38. Yes, negative 0.38. Two significant digits, two decimal places. So then to calculate pH, pH is equal to 14 minus negative 0.38. And that gives us 14.38. So that brings up the question, is it okay to have a pH that is greater than 14 and less than 0? And as a matter of fact, it is. I mean, many, many things have pHs that are less than 0 or greater than 14, especially if it's an extremely concentrated solution. So, there's lots of stuff dissolved in there on a strong acid. You're going to get a lot of ions, and that's going to lead to a very, very low pH. Just remember that our pH scale was made for beer. So that 0 to 14 is the concentration of acid that is the normal range for beer, not for, heavy-duty chemicals. Although I guess one would argue that beer might be a heavy-duty chemical. Anyway, so let's see. We were given the concentration of hydroxide. I probably should have written that first. 2.4 molar. And then to get the concentration of hydronium, we'll do 1 times 10 to the negative 14 over 2.4 molar. And this is going to be a really small number. So you've got a small number divided by a bigger number gives us a much smaller number. And that is 4.2 times 10 to the negative 15 molar. All right. Now we have magnesium hydroxide. The formula for magnesium hydroxide is MgOH2. So this dissociates into more than one hydroxide ion. This concentration is for the magnesium hydroxide. So to get the concentration of hydroxide ion for this base, we're going to multiply the 0.005, one significant digit. We're going to multiply that by 2. And that's going to give us the proper hydroxide concentration. Just to point out, this 2 is because of this 2 here. When this compound dissociates in water, it gives us 2 hydroxide ions for every 1 particle of the compound. So now that we have hydroxide concentration, we will calculate the pOH, negative log 0.01, right? OH, 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 hydroxide. This all is very, very logical. If you remember that bases make hydroxides and acids make hydronium. So the pH is, or the pOH is the opposite of the logarithm of 0.01. But pOH is the value 2.0 because we've got 1 significant digit, we need 1 decimal place. And then if we want the pH, we know that pH plus pOH equals 14. Therefore, pH is equal to 14 minus pOH. That gives us 12. So we know that the hydronium concentration is 1.0 times 10 to the negative 12 molar. I want you to think about that. This works when we have a base number that's a whole number. Okay, wrapping it up here. It's the last one I'm going to do with you. So we have a pH of 9.6. Before we solve for everything else, right, we needed pH, pOH, hydronium concentration, And bases are going to have a greater hydroxide concentration than water. So that's going to be greater than 1 times 10 to the negative 7 for hydroxide, which means that the hydronium concentration is going to be less than 1 times 10 to the negative 7. It has less hydronium than water has hydronium. Okay, so we've been given the pH 9.6 to start the problem. We will calculate the pOH. pOH equals 14 minus 9.6 for the pH. And that's going to give us a pOH of 4.4. Okay, I guess now I have to show you how to get the concentration of the ion from the pH or pOH, and it really is easy. So if you're given the pH of 9.6, you're going to do the exponential form of the logarithm. So you're going to do 10 raised to the negative 9.6, because we did the opposite of the logarithm. We did the negative log. So if you look on your calculator, you'll find your logarithm button to the next to the left of the 7. And then above that, for your second function, you'll see 10 raised to the x. So if we want to know if this is the pH, that can give us hydronium concentration. So let me clean this up. So what we're saying is, if you have the pH, the hydronium ion concentration is 10 raised to the negative pH. Therefore, if you want the hydroxide concentration, you would do 10 raised to the negative. Hopefully you are shouting. pOH. H, OH, H, H. Okay, so for this problem, the hydronium concentration is 10 raised to the negative 9.6, and that is 2.5 times 10 to the negative 10 molar. And then the hydroxide concentration, 10 raised to the negative 4.4, the pOH. And that gives us 3.98 times 10 to the negative 5 molar. Let's go back and check our prediction. It asks us to predict whether the hydronium concentration would be greater than that of water or less, and we predicted less. And if we look, our hydronium concentration is 10 to the negative 10, so that indeed is less than 10 to the negative 7. Okay, students of chemistry, that is pH calculations in a nutshell. At the bottom of your paper, you will find some practice that I expect you to do, and I will leave the solutions